You get it out of there?
Yeah.
Okay.
So this guy decides, well, I have that's close enough to oil. So he goes and gets the 5 gallon bucket. We've got the plastic bucket. It's on the floor, it fills it about halfway with the minerals.
So hard to
And he
do.
takes a piece of steel out of the oven at 1750 degrees. Really? And he drops it from here into this bucket. Plastic bucket, yeah. 750 degrees. So, supposedly this bucket sounds like, huh, sounds like a really bad idea, but okay, hold on a second. So I went and got the fire extinguisher. I was thinking over maybe here today, and I'm like, that's probably not quite far enough away. So I backed up, I'm like, we can just do it by hand. And I had on a shield, plastic shield, something, yeah. We got it to where it was like this far over top of the bucket, that he's dropping.
Show you how it matters 3 hours later.
And man, I took the fire extinguisher.
Is that funny?
It melted through the bucket, metal spirits went everywhere. It was hilarious.
That's my job.
Listen in. You didn't have a chance to do
And then that's when I realized that I got chewed out because I used the fire extinguisher.
Where
Because we had to pay her, I was like,
I
I
am.
wasn't qualified. No, I did, actually, I had to read fast the fire extinguisher.
Because you don't want to use one when you're not qualified. You don't want somebody else.
No, no, I have my certification on how to do it. I do.
Hey, next month is fire protection requirement.
I
The lights and fires is also.
Yes.
Actually, you can do it next
Fire, any kind of.
My lead reliability, my lead confidence, I do.
Like, we have to get a program.
I'm having trouble with the ambulances. What's
You know, when people like to grill, we have to do
I am rough, like, if I'm on my job, like, our job is rough.
It's not as bad as it's
Really just like 5.
It didn't matter if it was propane.
Let's look at me and say, what's the
I
salary?
guess they didn't have.
You would laugh.
You know, we're not mad, but I just missed
Which is a thing that everybody's telling me is
I was like, we're wearing 6.
So let's see, so we have 3 ways to exactly what I've already written.
That thing is I hate how close that was. It was like the,
On something you've already answered, right?
frozen turkey into the deep fryer.
Just send it back, I'm like, highlight,
Like, and I
send
have
it
to
back,
That's almost
right there.
Well, I just watched it. That was why I asked my question.
Like, here's like an example.
I'm like, this is gonna go badly. I'm gonna watch it.
Did you get out your camera at least?
Oh,
Color coded.
I had both fans on fire extinguisher.
Alright, so let's- so we'll pick back up.
That would have been great.
I did videotape one of the guys that decided to take a can of decrease.
So what also is in here is example 4.3. And, yeah. And so example 4.3 is this table.
That's a great idea.
This is what we had. And in example 4.3, the data, let's see, example 4.3, the data is just made up. So it's just a 3-factor experiment, A, B, and C. And they just made up some random data. They got 3 data points in here just like I drew. And so, so what I did, I just wanted to program in. It's not a big deal because we've already looked at the 3-way NOVA. But yeah, I wanted to program it so you'd have it, the example, and you can see, here's the 3-way NOVA from real statistics. It agrees with what's in the book. And so their data, you know, A has 2 levels, B has 3, C has 2, and then here's all the data. So you can see how I've arranged it, like the 96, 190, it's going to come across, yeah, 96, 190. So I had to lay the data out this way to use that real statistics tool. And if I use it in the row format, and then if you scroll down, yeah, this table here should look exactly like table 4-5. And if you see, look like at the p-values, they're all the same, except for this one, which I was amused by. See, all of mine were the same. So then I wondered if that one was a typo in the book. You know, nobody's gonna. Most people don't pick through a book that carefully. But if you look, my P's, this one, that one. Well, they got 0 here, which you can see that's 0. But there was something a little bit different about that one. So, but maybe their ANOVA calculates things a little different. So that's what the A and C interaction. So anyway, the book goes through and explains example 4.3. You know, they've just got this made up data, and they've got some response plots, and they go around and conclude the same thing that let's see, B and C mattered, and then there was the interaction like we've talked. If B and C mattered, you expect to see the interaction. So nothing startling about this. It's just you know, the use of the three-way ANOVA on an example you got that you can go back to and look at. So again, I did it the same way, selected the whole table, did the three-way ANOVA from real stats, and said the data was arranged in rows and did the 5%. Okay, so that sort of brings us to your tool. Okay, now I've got my tool. Okay, now let's see. So and we've seen it in 4.3 and it worked. And see, remember B and C mattered, and we got a little interaction here. Okay, so now the question is, do we want to do that? Well, I don't know. Let me read you this. So maybe I should cover section 4.3 first. Yeah, I'll read you this. Okay, so let me read you this little sentence from this GraphPad user guide, and let's see what you think. It says, a GraphPad Prism does not perform three-way ANOVA, but many have suggested that we add three-way ANOVA to our future versions of the software. One reason we've been reluctant to add three-way ANOVA to our programs is that it often is much less useful than most scientists hope. When three-way ANOVA is used to analyze data, the results often do not answer the questions the experiment was designed to ask. So let's look at an example. And this example is in the book, in their book, but I'm going to go through it. So they've got an interesting example. They're looking at mice, and their question is, how does low oxygen levels influence the growth of blood vessels in the brains of these mice? So the words in this thing, they got let's see, angiogenesis, and that's the. Sometimes it's good to have examples outside of engineering, you know, it makes you think. So this is the growing of the blue blood vessels. Let's see. And then there's hypoxia. Okay, so this is low oxygen. So they're now what are they caring about? Well, they see that there's a gene. Okay, that is required to get angiogenesis. All right, so they got this gene that's required for this, and so what they're going to do is they're going to get some mice, and they're going to get they're going to have two different genotypes. Okay, number one, with the gene gone, right? Knocked out. They call it KO. And number two, with it there. Regular old wild type mice. Okay? They call it WT. Maybe I'll erase my 12 trees. Forget the words, but okay. So hey, this is one of our factors, right? Going to care. Does genotype matter? That's the fact. What? That's the central question of this text, right? Does this gene matter, okay? And what's one of our other factors? Well, right? Yes, okay, that should be factor 2. And our third factor, which kind of, you know, isn't obvious from things I've said, but obvious from thinking, is time. Okay? So they have a 3-factor experiment. We're going to have 2 different genotypes, 2 different hypoxias, which means regular air, okay, and low O2 atmosphere. And then time, they're going to have 3 times. 1, 2, 3. Where it's getting later. So we're going to put some mice in regular air, and we're going to put some in the low air. We're going to measure the amount of blood vessels in their brain at 3 different points in time. Make sure I said it right. Yeah. 1, 2, 3. Yeah. Okay. Yeah. Here. Yeah. 1 week. 2 weeks. 3 weeks. Okay. So this is experiment. So right offhand, you know, you could say, oh, this is 3-way ANOVA. Let's do it, right? I got 3 factors: genotype, hypoxia, time. Let's do a 3-way ANOVA. Okay, now let's do it. And let's look, because I think this helps. Let's look at what A, B, and C are, and A cross B, B cross C, A cross C. Let's look at what each one of them is so we can understand these things. Because I for me at least, it helps to clear it up. So let's see. So A is the effect of the genotype. Okay, let's see. What did they say about that? Okay, so in this, the null hypothesis is that you know, so the H0 is, you know, regardless of anything, the genotype doesn't matter, right? Yeah. So you would say it, you would state it right, whether you know, whether it's you see low O2 or not, and week 1, 2, or 3, you know, genotype doesn't matter. Well, let's see. So one of the comments, and this is where they're starting to explore this, is there's a problem with this, right? I mean, we've mixed in hypoxic and non-hypoxic groups together, right? And so we kind of muddled the picture already, right? Because we're just asking, does genotype matter? But if we just test the A hypothesis, we've mixed in this variation, and we've actually mixed in the time kind of stuff too. So you know, it's a bit of a muddle. Alrighty, that's fine. B, hypoxia. Okay, let's see. Let me see what their statement is on that. Let's see. The null hypothesis is that both genotypes and at all time points, the average result is the same, whether you're in low or not. Okay. Well, so let's see. Yeah. So we've mixed again in the hypoxia, whether we're so the H0 is KO or WT, so knocked out or wild, and whether it's week 1, 2, or 3, hypoxia does not matter. Well, again, we've kind of muddled the results. We're mixing in knocked out and wild type. We know hypoxia affects the wild types anyway. We're getting worse. So this doesn't, you know, what I'm saying is these things aren't going to get evaluating these effects. It's not going to help us. See time. So we're saying, okay, the H0 there is that whether we're low O2 or not, and whether we're KO or wild, time doesn't matter. Well, you know, this one is particularly worthless. And we know time matters. I mean, the growth of the blood vessels. So of course we're going to get a low P here, and we're going to learn a whole lot, aren't we? So you can already see we've got a problem with this design of this experiment already. Okay, well let's go even further and see what happens, and this will help us understand these interactions. So let's see. So let's think A cross B. So what does A cross B mean? Let's see. So A and B, well I've got it written here. So A is genotype, B was hypoxia, C was time. So I'm looking at the interaction A and B. So this says, so this kind of, the way you would read your null hypothesis here, it says that maybe a good way to state it is hypoxia or not has, maybe this is a good way to work, same effect on the knocked out or wild type at all points in time. Okay. So let's see. This is kind of what we're looking at, right? Yeah, except we know, this is one that seems to answer the question. We've eliminated C, interaction A and B. Okay, we're not worried about time. Let's see. So, but if we're mixing in the knocked out and the wild type, and then we already know hypoxia affects the wild type, so we're still kind of muddling it. But this is really kind of the one we're looking at. So we've stuck what we're really looking at down into an interaction already. That's the one question we're asking: does the hypoxia have or not have an effect through time? Let's see now. A interact with C. Let's see. So this one doesn't have hypoxia. Okay. So this is genotype in time. This one just doesn't make any sense at all, right? I mean, the whole thing is we're looking at hypoxia. It's not even part of this interaction. So in time. I mean, are you saying that the KO and the WT are going to respond differently in time? Yeah. So the null hypothesis is that our null hypothesis is that phenotype is the same through time. Well, yeah. So that's sort of weird. This one is even worse. Okay, so now we've mixed hypoxia and time. Okay, well, so we're asking, the null hypothesis is the effect of low oxygen the same at all times? Well, again, like before, no. Okay, so we get a low P, we haven't learned anything. And then now you go here, A, B, and C. What is that? I mean, hypoxia and time and genotypes are all parts. It's hard, it's difficult to say. So you can see how basically we pushed down what we were looking for down to an interaction, and we really haven't concluded. We've muddled the waters up here. So what would have been a better approach? We could have used a three-way, but what do they suggest is a better approach? Well, they say, well, look, what the problem with this is, the whole problem is that we're mixing in the guys in regular air, right? Who cares about the growth of the blood vessels in the regular air guys, as long as we don't, that's the control group. So if we do put knocked out and wild type mice in regular air, and all of a sudden we see they're growing a lot of blood vessels, that means we've got something wrong with our mice population, right? Because the whole idea is that does the low oxygen make a lot of blood vessels grow, and depending on whether you've got the gene or not. So if we got them in regular air, it's not low, and all of a sudden blood vessels are growing, we've messed up. So why don't we, what they're suggesting is why don't we just throw all the control mice over there, the ones that don't have the gene, the ones that do, let them sit for 3 weeks and see if they get blood vessels, and if they don't, or if they get, it's just the normal increase or whatever it is, then that's fine. That means our mouse population is fine. Now let's go over to our experimental population and just do what we wanted to do, which was factor A is genotype. Yeah, that was the simple question we were asking. And then factor B is time. And let's look at only the hypoxia population. Okay. So now we've reduced this 3-factor to a 2-factor with the control group. And all we've got over here is the A cross B now, which is says that the difference between knocked out and the wild type is the same at all times. Okay, alrighty. P-value's large, you don't need to check out some multiple pairs. So that's important, but this, that was our big question. Did the genotype matter to the production of blood vessels? So what their whole point was, well, hey, you could have done this 3-way ANOVA and maybe kind of dug out your answer down there in that A cross B interaction, or we can throw everybody over in the control group, make sure they don't anomalously grow blood vessels, do a 2-way ANOVA on just a subset of the data, and really get to the main effect up here, which is what we were looking for. So their point is maybe you don't want a 3-way ANOVA because it muddled things. You had too many factors going on in there, and we could eliminate it by a different approach to the experimental design. That is, control group versus the hypoxia group, which is really where we're looking at things. So perhaps that's why they say we're not doing a 3-way ANOVA. Now maybe that's because they're just lazy or something. I don't know, but I can see that point. Now, but then you might argue, I still want to do 3-way. Oh, okay, all right, that's fine. Is there another way to do it besides this real statistics thing? Because the real statistics might not be what you want to do, because maybe it's hard to download or whatever. Let's see. Well, how about this? Remember, before I switch, let's see, we had B and C and an interaction between B and C in example 4.3. All right, let's see. So this is back to example 4.3. And look at the weird way I've laid out now what I did on example 4.3. So I took all of the data that was in that table, each of the 3 blobs, and I just laid it out into one giant column. And over here, I've assigned what it was, right? A111, A11, let's see. So those first 3, those are the 3 data points that were the 3 samples in the first treatment, where A was 1, B was 1, and C was 1. Then the next 3 data points are A1, B1, and C2. So that's all I've done, laid out the whole table, each of the 3 samples under each treatment together, but I've identified them with this code, right? The code is what they were. Okay, then I've created A times B, then I've created A times C, B times C, and A times B times C. All right. Now, instead of doing an ANOVA, let's just do a regression on this thing, a linear regression, and find out, is this important? Is that important? Is that important? Is that important? And let's see if that works. Okay, let's see. Okay, so we do a linear regression. Linear regression's in Excel, right? We just select the whole data, say linear regression, boom, there it goes. Give you, the 5% just like we did. Well, let's see. Did A matter? No. And remember, you can either look at the p-value, or you can see did it capture 0, whichever way you want to look at. So let's look at it here. A didn't matter. B, yeah, it's less than 5%. It mattered. C, yeah, it's less than 5%. It mattered. A times B, no. A times C, no. B times C, no, we lost that one. So it's a little bit different approach. But we were able to use this approach and still find the two main effects that we were looking for. So it's another way to analyze this without using the three-way ANOVA. Is it better? Well, it's different. Depending on how we code it, I could actually make it get closer results. And I'll revisit that in one of the future chapters. And let's see here, what did I do? I didn't get the I didn't select the cross terms. I just selected the main ones. Let's see, did we get anybody? Yeah, we got B and C. Yeah. So here I just did a simpler regression where I didn't get those other columns. And so there is hope still for another approach if you don't like this three-way ANOVA, another statistical approach that will let you dig some of these effects out, depending again on how you laying your data out like this. Now, the traditional way, they call it effects coding. They'll do like if you had 3 effects, they'll do it this way. They'll use 2 vectors. And we'll come back to this again in the future. So I just wanted, it was not my words, remember coding? And you can see how it worked. So if they had 3 factors, say A, B, and C, and one of the ways they might do it is let's see, A and B. So they use 2 vectors, so they would be like that. If you had A, like this if you had B, and like this if you're in C. And so you're using 2 vectors to identify 3 things. And so you'll see that in some of the examples. Like I said, we'll come back to that. But just I wanted to introduce it here because it segues with this, but we're not using it here yet. So there is another way. Okay, so that's there. So now, what's the last topic then that I would like to get you to familiar with here before we leave this? Yeah, that one, example 4.4. All right, then that should be everything. Yeah, all right. So example 4.4 kind of goes into this whole bit that we're talking about with these error, the size of the error, the mean square error, and these interactions that we looked at in these three-way ANOVAs. So one of the things, if you look at section 4.3, it's a little tiny section stuck in there. Okay. Got example 4.4. So what happens is they start out and they say, hey, look, one of the things in all the examples we've done so far, we've assumed 2 or more samples per treatment. Okay. Right. Example 4.3 had 3. My car example had 3. Remember, and we talked about the word balance. Had the same number of samples in each of the treatments. And remember, it was, and the reason, why do we assume this? Words are so we can calculate random error. Okay, and I emphasize that at the start when I do that table. If I don't have more than 1 data point under each treatment, how in the world can I calculate a random error? Because everything is just going to look like a treatment. And so I'm going to assume it's a treatment, or my mathematics is going to assume that. So I can't, if I don't have at least 2 or 3 or more, I can't come up with random error. How else? Okay. But what's the problem? Well, so we got lots of factors. Right? Let's say we got we got 4 now. A bunch of factors. Oh, no, we got 2 treatments. I mean, we got 2, we got 2 levels. Okay, it takes a long time to do these experiments. Oh my gosh, we just, cannot do it. Fiscal year is ending, we just can't get the darn data. So what can we do with lots of factors, lots of levels, not enough time? Okay, what? Help me. Okay. Let's use, the higher order interactions as a surrogate error term. So just like when we were asking, is our mean square error of the treatment big compared to the mean square random error? Well, okay, let's just ask if the mean square error of the treatment is big relative to all the little interactions. Well, that's okay, So, because we know if we have lots of factors, right, then we're going to have lots of interaction terms, right? We're going to have ABC, BCD, ACD. We're going to have a lot of them. So we're going to have a lot that we can throw in to this error term. It's going to have lots of degrees of freedom. We'll be able to, bolster it. It's not going to be so tight, so big that it overwhelms our F statistic. And besides, we just saw from the previous discussion, what do those higher order interactions mean anyway? We've also seen from our ANOVAs that sometimes they're hard to even dig out, or depending on the random error, sometimes they show up, sometimes they don't. So these higher order interactions, A cross B cross C, A C D, they're kind of dumb anyway. Why don't we throw them in an error and use them in a way that's useful to us? It's even we like we said in that example, what is A cross B cross C? Really, we couldn't even really tell you what null hypothesis it was testing. So why not use them in an error term? Okay, so if you look at example 4.4, and we'll pull it up here in a minute, what does it have? Well, it's got it'll have a small number of relatively small number of degrees of freedom in the error term. Okay, which means then that always, F, which is going to equal MS treatment over MSE, then if there's small degrees of freedom, that's going to be big, which means that F is going to be small, which means we don't learn anything. We don't reject any null hypothesis, we just always say nothing matters. So what example 4.4 is going to show is, hey, why don't we just try our best to get the main effects, the A, B, C, D, and the first order interactions maybe, A cross B, B cross C, those, and let's throw all of the higher order terms into this surrogate error. So let's see, so what are they doing? Let's see if we can look at it and see it in the context of their example. So what they've done in example 4.4, they say you've got an alternative approach to your experimental design. That's what this class is, right? So we've got four factors, A, B, C, and D. And they have little a, little b, little c degrees of freedom. We got 3 levels of A and B. So A is 3, B is 3, 2 levels of C and D, and 1 data point at each treatment. So our total number of treatments was 3 for A, 3 for B, actually not, yeah, 3 levels, but the degrees of freedom are always 1 minus. I should have, yeah, it's funny, degrees of freedom is always 1 minus the number of levels you have, remember? Yeah. And so the total number of treatments are 3 times 3 times 2 times 2. Now 36 treatments if we do this. Okay, so let's look at what we've done. So let's see. So if we have 36 treatments, let's see. We start looking at our degrees of freedom, and we say we get down here, and since we've only got one data point for each treatment, we can't get an error term, right? Like I said before. So let's make the error term with all these higher order guys. Okay, so let's see. So in the error term, we've got 16 degrees of freedom in the error term by using all the higher third order interactions and the fourth order interaction. Okay, now, or could we do a different experiment? Well, yeah, let's see. We got our 4 factors still. Let's just do 2 levels of A and B and 2 levels of C and D and have 2 data points for each treatment. Okay, so all we've done is dropped a level of A and B. All right, so you look now at your degrees of freedom. Yeah, we dropped a level for A and B. We go down here, we got the higher order, the first order interactions. These are the main effects, remember? First order interactions, third order, first order interactions, second order, and third order. And then we've got 16 degrees of freedom. So still the same number of degrees of freedom in our error term, but it's a real error term now. It's not a combination of these higher order terms. It's the actual random error because we have two data points or 2 samples for each treatment. We can actually estimate the error. And so, and plus, let's see, we had 36 total treatments over here or experiments to run. We only had 32 here, right? 2 times 2 times 2 to the 4th times 2 data points, yeah. So the point being, this choice is better than that one because you did 4 fewer experiments and you were able to actually calculate an error term because you had 2 samples per treatment, and the only thing you lost was the middle levels of A and B. This is kind of hinting at what we're going to be doing in the future, trying these kind of ideas. And so to choose this design over that design because you're able to got the same degrees of freedom in your error terms, but it's an error term estimated from the actual error between the samples, not from this conglomeration of these higher order terms. And then I guess you might actually be able to see some of these weird interactions, even though again we'd have a hard time interpreting those.
So you want all your degrees of freedom to be equal? Does that have, it makes it more balanced, or?
You would, it's better, the point is it's better to do fewer levels and have less degrees of freedom, but have more data points in each of the treatments so that you can get a better estimate, a better handle on your random error. And so this first one, so it wasn't that the degrees of freedom were all the same, it was just that we were able to eliminate a level in B and A and do fewer treatments and trade it off for doing more do more than one sample in each treatment. And because of the fact that we had more than one sample, we could calculate an error term, which we believe is a better estimate of this error, better estimate of the MSE than this conglomeration. Although this is okay if you had no choice. It would be okay to use that for an error if we had no choice. But here we're at the front end. We're designing our experiments. We're going to make a choice. We're going to choose to do fewer levels and have a good error term. That's what we're trying to get at. So, one of the things I might say too is this goes back a little bit to the biology example. It's like I might try to design an experiment that doesn't have 4 levels. Get the control and have 2 levels, or somehow if level A is something, well, I'll do a 3-level BCD experiment over here and a BCD one over here, and kind of try to separate them out some way. Try to not statistically study 4 levels all in one analysis. Do some separate analysis or something. That'd be a little better approach. But I guess too, this example is trying to justify from a mathematical design of experiment approach, why you might do that. I think it's justifiable from a logical approach. Fewer levels, but more samples per treatment seems to always make more sense than spreading out your levels and taking less data points. So I mean, I don't know that we need to have a design experiment calculation to show us that kind of, to me it's logical. Yeah, I'd rather, it really bothers me not to repeat things at least once, because of an outlier or something like that, it's difficult, difficult to draw conclusions when you got something anomalous that happens when you only take one data point. So I would probably favor this anyway, and maybe what I'm saying is intuitively, this is verifying mathematically what we kind of already know intuitively, because I'm saying if I only take one data point, intuitively I can't evaluate the random error, can I? But if I take 2 or 3 data points, I can intuitively evaluate the random error, and I can show mathematically that, yeah, I can calculate the random error. So I guess that's really what this is kind of saying. It's, yeah, mathematically it's a good idea to be able to calculate the random error, and intuitively, experimentally wise, we think it's a good idea, because with just one data point, you're just, well, it's one data point. If it's anomalous, or appears anomalous, is it a result of your treatment or not? And that's why you want to go back and repeat it. But if we design the experiment ahead of time and go ahead and repeat them, we don't have to, especially if we're in an environment where you can't go back and repeat them, or it's expensive to go back and repeat them. It'd been nice to have thought of this ahead of time. So that's kind of, I think, what this is showing. So hopefully this chapter inspired you to think about the math, do I really want to do some of these statistical techniques? Or be careful just flinging data into a table and push and go. Be careful you can you can articulate what it is the results are showing you, or that you understand what some of these things mean, and then evaluate whether you really want to do your experiment that way or not. But if you do, okay, we've got this 3-way tool, and then what we'll do next time is when we've got these kind of factorial explosion, how can we deal with it with the presence of background variables, or how can we do it in an efficient way? Because we're starting to get an explosion, and then once we get background variables, now we're getting it even worse, because we've got an explosion of factors with blocks. So what kind of things can we do? And we're going to wind up doing some things like this, where we have minimum and maximum values at certain levels, and then taking steps from that, from there to further investigate once we find out what the main effects are. So I guess next week we got fall break, and I was going to go ahead and put the I said the midterm online, and I'll email you too through Canvas. I'll try that, and we won't even discuss when you turn it in. Just work on it if you want, or don't work on it if you don't want. Don't worry about that, because you got to focus on your capstones, which are what coming the 3rd week. Is that, am I right? Yeah, and she hasn't picked a day yet. Is that because that's what you were discussing, to know 1 or 2? Okay.
Last week.
That's what she told me too, but I heard Greg say.
The last week of October. What day is she looking at?
She's not, she wanted to go 1 or 15. She needed to reserve 1 or 2 days.
And was she going to take a Friday from us, or do you know?
So now it's the week of the 30th.
I guess Tuesday, Wednesday, or Wednesday and Thursday.
Yeah.
Okay.
But Dr. Saunders is leaving us Friday.
Well, I guess we'll find out.
So we'll know if it's the week of the 23rd or week of the 30th.
Would you bring with you, by the way?
I've got a trip.
I'm gonna bring
I can tell only 2, I don't know. She'll decide soon. And I'm not deciding whether to do it.
I
One of
will not be able to
but
come at all.
that's all right. I'll tell him.
Yeah, I will feel, I'm relying on you too.
Yeah. Hopefully this inspires you to think about this stuff. It's confusing somewhat, but